To be given by Artem Pelenitsyn from Purdue University, and his talk is entitled Approximating Type Stability in the Julia JIT.
Right. Hi, everyone. Thank you for accepting this talk and this short work in progress, rather. I am working with the Julia language for some time now, so I want to share a little bit about the language itself and most importantly about type stability property that I've been working about. So I will start with a simple example that shows why this property is important in Julia. In this code, I try to sum a vector of some kind of numbers, and I leave out, so there is just a for loop that goes over the vector and, summed it. The only bit that I leave out here is the initial value. So let's, I performed two experiments here. I replaced the question marks with the integer 0, and I ran the function with the vector of floats, and it runs in 24 microseconds. And the second experiment is that it's the same vector, but the question marks is 0, is the floating point 0 now, and it runs more than twice as fast. So there seems to be something going on with optimization, or rather something going wrong when you have this mixture of types, floats and ints getting together. So when Julia programmers hit into this kind of performance issue, they would usually call a utility called code-word type, which prints out an intermediate representation of the compiler, and they just look, so there is a rather low-level sort of SSA-like representation. It's a long chain of assignments, basically, to some virtual registers, or called slots. And what people usually do is they try to look for the visual cues in this form of types pointed in red. So every slot you will notice be typed or type inferred, and this particular method instance is type inferred for the input of type vector float. So it's important that we know what kind of input or input type we compile for, and under this assumption we get mostly blue types. So blue means good, except for the accumulator variable is its type rather is painted in red, which means the compiler doesn't know really what it is, how to store as a float or as an int, and that's why the performance degrades. So now scaling back a little bit out of this example, the reason for this, so let me try to explain it in a couple of slides. So first is Julia, important fact, Julia is built around multiple dispatch, so every operation in Julia goes through the dispatch mechanism, which means that there is a method table for every function. So for example, the plus function has around 200 methods defined only in the base library, and there is packages defined more. And so it will try to dispatch to the most specific or most applicable method in the library. So the crucial way to run fast in Julia is to perform devirtualization, so remove those method dispatches and try to do what we call direct calls. So some time back we wrote an OOPSLA paper about how JIT operates exactly, and the way it operates is, given some concrete input types, it does some kind of runs some kind of type inference algorithm, and it tries to devirtualize as many calls as possible. And those devirtualized calls are essential for all the other possible optimizations you can think of, like inlining or unboxing. So all this is predicated on knowing an exact exact method that we will call at runtime. So we sort of come to the conclusion that this property about being able to infer a most precise type or some precise type, right, for a method call is paramount, and it enables the virtualizations and all other optimizations as well, or many other optimizations as well. So type-stable methods are methods that possess this property that given concrete input types, it can the compiler should be able to infer a concrete return or precise return type. And the desired property is full devirtualization, so we have no dispatched calls at all. And these methods, the methods that are fully devirtualized, they can only call type-stable APIs. So that's one of the theorems from that paper. But that's not the point of today's talk. Today, the point of my work these days is we are sort of unsatisfied by the state-of-the-art in Julia practice. So that's what programmers do. They reach to the Codeword type utility, and also the Tupsla paper also deals or based off of this intermediate representation. So our goal is to be able to reason about type stability on the source level and not go into this horrible mess of low-level instructions. So the algorithm we sort of go into, or we try to propose, is based on this observation that the naive inference that, we start with a concrete type as the input and we try to carry that information to the output works in the simplest cases maybe, but any operation, as I said before, goes through the dispatch. So really, in order to be able to reason about concreteness or abstractness of the return type, you have to be able to devirtualize, or at least you have to be able to reason about what you will dispatch to. So in this case, this plus can be one of those 200 pluses defined in the standard library. So in order to be able to resolve this or have some information about the return type, you have to reason about types of inputs. And so it boils down to basically it boils down to the full problem of type inference. But type inference is already implemented in Julia, as we noted before. It acts on the intermediate representation, but nevertheless, so we don't really need to re-implement type inference. We just need to figure how to supply those concrete input types for the method that we are interested in. And this is the way we arrive at the sort of general framework that we propose here, is that if you have a method that you want to analyze type inference for, you will extract its type signature, its input type, and you will try to exhaustively enumerate all concrete type C that are subtypes of the signature, and then you run Julia's type inference for the pair method and the concrete input type. So the Julia's type inference, again, is a decision that we sometimes have to defend, but the reason here that we don't build our own type inference is that if we build our own, it will not necessarily agree with what Julia does at runtime, and we really want to be able to predict what Julia's runtime does, so we rather reuse what it has for type inference baked in. And the actual sort of hard work, heavy lifting of this work is that this rather innocently looking second step, which says, well, how do we extract all those possible concrete types of the signature of the method? So Julia has a rather rich type language for a dynamic language anyway. So we already have seen nominal types, so types like ints and floats and vectors. For those, it's easy to find subtypes of those nominal types. So, for example, number has these two subtypes, and if you want a concrete type, you will have to iterate the application of subtypes. So you take subtypes, apply it to number, and then you apply it to complex, and then you apply it more and more, going down the subtype lattice. And when you hit the bottom, which means you hit a concrete type, then you can stop. And the nice property of Julia's type system or type setup is that concrete types cannot be subtypes. So you just start from from some point in the subtype type lattice, and you go and you try to collect all the leaves basically. So this works nicely for the built-in subtypes function. It works nicely for nominal types. It has nothing. I have no idea of the structural part of the type grammar, which is unions, tuples, and so-called existential types. So we will have to extend the subtypes utility with what we call direct subtypes, which is also a bit more precise name for this utility. We still will have to iterate after we do one step of subtyping. So we, for example, union of number and char. Direct subtypes of those there is number and char, and then we'll have to recursively iterate over those subtypes. So this union and tuples are rather simple examples. So I'll switch to existentials here. So existential type is a type, for example, vector here, vector t, where t less than number is an existential type that will match all possible vectors that were instantiated with number types. So for example, if you call a function that declares this type as an input with a vector of ints, it will get called because vector of int is a subtype of this or vector of int 32, for example, is a subtype of this this existential type. So you'll notice you'll have to instantiate with all the possible subtypes of the upper bound here, the number. So T will have to enumerate it, with all possible subtypes, not just the direct subtypes. And that's a little subtlety, but we, as I mentioned before, we are anyway looking for leaves, and that means that we need to implement the all subtypes utility anyways. So that's no issue. So given a reasonably tight upper bound, we should be able to just enumerate this exhaustively. So the real challenge is comes when we don't have a concrete upper bound. So when in the methods in the Julia APIs, you would usually see just a vector input, and vector means vector t, where t from bottom to any, which is basically anything that any Julia type would suffice to match this type, right? Or vector of any Julia type will suffice to satisfy this type. So the issue in such types, there are several issues actually with them, but the simplest one is that you can recursively instantiate parametric types if you don't have a bound on parameter or any other bound on any. So you can just go into loops, start and trying to find and trying to enumerate all the possible concrete types here. So we have a couple ideas how to handle this. So first, you will notice, as usual, not all functions actually depend, or return types of not all functions depend on the inputs. For example, if you compute a length of a vector, length will always return int, no matter. So it's actually possible to call Julia's type inference with an abstract type, and it will, in some cases, for the functions that we call type constant, it will be able to return concrete types, and that's enough to handle this kind of cases. And the second idea to handle any is actually comes from this observation that we were trying to go from top to bottom, and we rather try to start from bottom, start from leaf types, and not go anywhere. So in that case, we just don't run into this issue of going into loops. Yeah, indeed, we can sample types from some input, some packages, see how we can run the tests and see what's being used, what types are used to instantiate all those methods in the test suites, and we can collect them, and we can then use them later on to enumerate possible input types. So that's what we do, and that's what we call approximation, because we can not enumerate. So by sampling, we necessarily approximate. We can't sort of exhaustively enumerate all possible input types in those cases. But our preliminary evaluation against the earlier Uppsala work shows that the numbers that we compute for type-stable methods, the amount of type-stable methods in those packages that we analyze, so there is just some 10 popular Julia packages, are actually pretty close to what we saw when we did tracing. So when we just ran tests and see if the whatever test call is stable or not. So that's where I want to leave this presentation, and I'm happy to take any questions. Shouldn't stop sharing the screen if there are questions about slides. Get back always.
Do we have any questions? We have one question. Thank you.
Can you go back?
Do you want to come up here? You want to come up here?
Yeah. Oh.
Now that we looked at all the machinery for finding concrete types, can you go back to the slide where why we needed them? I sort of like lost track of the purpose of finding all of these. So
right.
We need to find.
Yeah, that's how we.
A single concrete type or every concrete type?
So ideally, every concrete type. Yeah.
And then based
that's
on
how we,
all concrete types, you can then say that this is stable if you've seen everything.
Right, exactly.
Thank you.
Any other questions? If not, then we will conclude this session. Thank you very much, Artem.
Thank you.